One of the guys on the group asked how to solve these tasks with tanks. So I want to record a short video where I'm going to show how I'm doing that, how I'm setting up the PID controller and so on. So it is already solved. It's working properly. The PID regulator is already tuned, and this is how I do it. So first of all, of course, I need a connection from the PLC to the factory I/O, and I have already done that. If you do not know how to do that, have a look at the previous videos. I've also created the tag table, so I've got all the tags already prepared. So if you also don't know how to do that, go to the previous videos. It's very simple. Now, what I want to do, first thing, I want to get the inputs to the PLC and I want to scale them. And now I don't write the program in OB1. I always try to sort the stuff inside of my program. So I'm going to create inputs FB. This is going to be function block, and I'm going to call it from OB1. Inputs IDB. Okay, and now, so first thing I'm going to do here, I'm going to normalize and scale the inputs. And for that, I'm going to use norm x block, and of course, as an input, I'm going to use this level, and here I'm putting the limits in which it is coming. So the level meter comes from 0 to 10, so this is what I put here. And now I need a tag for normalized value. So first I'm going to put it to temporary variable, so t underscore level meter, and it has to be a real value. All right, and now I'm going to use a scale x block to scale it from 0 to 300, because this is how the maximum level is, 300 centimeters. I guess in this case it's not an engineering value. Usually you should use either meters or millimeters, but this is how it is in factory I/O, so this is how I'm going to use it as well, so that it stays consistent with the project. So 0.0 to 300.0. And what I usually do, I create a DB, a global DB, and then I can reach for the processed values already and use them all across the program. So I'm going to create an inputs DB, because I don't like to use this memory bit area. I don't think I can organize it very well here. So I'm just creating a data block and inputs DB. And in the inputs DB, what I'm going to do, I'm going to put the level meter real, and another one I know I will need is the knob setting. So So I will need a set point. So what I do now, I just drag and drop this guy here. And another thing I'm going to do, I'm going to pretty much do the same thing for the knob setting. So copy paste, and I'm going to create another temporary variable. All right, and I just need to change the tags. So set point, it's also coming from 0 to 10, and I want to change it to 0 to 300, of course. This, and all right, so now we've got the inputs. Of course, we can test it. So I open the fill valve, and as we see, the level meter is changing. So this is working properly. So that's okay. And now let's see how the knob is reacting. So let's play a bit with this one, and it seems like it's working properly as well. So next thing I want to do, I want to put a regulator in. So before I do that, I actually need to make some research. I've done the research already, and I know that to add a PID controller, the one that Siemens provides us with, I need an organization block that will be called in a cyclic interrupt. So I need to create a cyclic interrupt organization block. So I'm creating a cyclic interrupt like this. I put the cyclic time 100 milliseconds. You can make it 50 milliseconds, whatever you need to. For me, 100 milliseconds is all right. So I'm creating this one. And again, I don't want to put the regulator directly inside of the cyclic interrupt. I want to put it in an FB so that the code is kind of organized in a way. When I have one regulator, it wouldn't be a problem, but say I have 100 valves like this to control, I want to keep them organized in a nice structure. So I'm going to add a new block, and it's going to be function block, and I'm going to use level regulation. And now what I want to do before I do the regulator, I want to put the set point value and the process value on the display. So let's go to instructions, let's go to conversion operations, and I'm going to have to round the set point and the actual value on the display. I'm going to have to round the real value to integer value because this is what the displays require. So inputs db, level meter, and I'm going to use this output. So and the same kind of block Alright, now I will have them on the display, so I can finally get to the regulation. Okay, one more thing I forgot to do is I have to put this here. I have to call it from the cyclic interrupt. What I need to do, I need to select a compact PID and put it here. So now I can choose what kind of instance I want to use, and this is kind of complicated in this case to use a multi-instance DB. Normally I would do that if I would be working with any different kind of a block, but in this case I'm going to go for single instance. Let's call it like this. And now the PID is created. Now we have to set it up. So what I need to do, I need to give a set point, and the set point is of course going to come from the knob set point, and the input, so the value that we're going to regulate, is going to come from the level meter. And now the output. What we're going to do, we're going to regulate how much the valve, the fill valve, is opened to reach the certain set point in the tag. So we could just put the output here, but I don't really want to do that. What I want to do is I want to create a temporary variable, because the output here will be from 0 to 100%, and the regulated value, so the valve openness, is from 0 to 10. So I will need to divide it by 10 later on. So real So I'm just going to use the multiply block and 0.1 and I don't remember the name of this tag. And now, before I start to try to regulate something, I might want to do some pre-commissioning work. So what I'm going to do, I'm going to control the level. We don't have the level, so let's go for volume. Input output parameters. We're not going to use peripheral inputs outputs, we're going to use the input and output. And process high limit is 300, no scaling and no warning. Output value, high limit is 100%, low limit is 0.0%. Sometimes you will have to limit it. In this case, there's no need for that. So we have 100 and 0%. And PID parameters. Well, honestly, the only thing that I might want to change here at the moment is the controller structure, because right now it's PID. And I think the better solution for this case would be a PI, so proportional and integrating regulator. And the reason for that is that if we have noise on the input, we could get a lot of noise on the output, because this is how the differentiating part of the regulator is working. It reacts very fast to the change of the value. So for now, let's leave it as PID, but in the future, I might want to change the structure of the regulator from PID to PI. For now, let's leave it like it is. All right, so we're good with that. Let's make a download to the PLC and see what's going to happen. So now let's play with this knob a little bit, and we see nothing is happening. I'm just changing the value here, so I'm changing the set point, but nothing is happening. That's because first we have to commission the PID controller. So I'm going to press this button here, and it's opening the commissioning window. And what I'm going to do, I'm going to press this start button. This is the first thing. And now I have to press the tuning start. First, we're using the pre-tuning mode because this is the right thing to do. Next, we're going to do some fine tuning after the pre-tuning is done. Okay, so the system considers the tuning to be done, the pre-tuning to be done. So what I'm going to do now, I'm going to open the discharge valve so that the fluid is going to go out from the tank, and that's when I'm going to start the fine tuning, because we're going to need some disturbance. So let's start the fine tuning and see how the system is going to behave. So fine tuning is in progress. It's going to take a while. And what I actually see here is that the regulator is acting in a way like it switches on, it goes at 74%, and then it goes off, it shuts the valve off. It means that the D part of PID regulator is quite strong, and I don't want this kind of behavior. Like, I want the valve to be constantly open for certain period of time. So what I'm going to do, I'll just go to the PID parameters, and I'm going to switch the tuning rule to PI, and let's see what's going to happen now, and let's see if the regulator is acting more appropriately. All right, it says that the system is tuned, but well, did it tune it in optimal way? I don't know. Actually, I don't think so, to be honest. But when it comes to regulations like this, it doesn't always have to be perfect. And sometimes it also depends what you want to reach, because in some cases you would want some over-regulation and you would want to get to the set point faster. In some points you don't want any over-regulation and you do not care about getting to the set point a bit slower. So how you set your PID is the matter of a few factors like this. Anyway, to check if everything is working like we want it to work, let's change the set point and see how the system is behaving. Okay, so it seems like it's getting to the set point with very little over-regulation, and well, it's good. We can change the discharge valve openness and see how the system is changing its behavior, because PID is the kind of controller that will adapt to this kind of situations. And you should keep in your mind that PID is a very useful tool. It has a lot of applications possible, but it's not the only type of regulator that you can use in your applications, especially when it comes to reaching the set point from a very far distance. So you can use different applications. In this case, PID is good enough, I would say, so we don't have to search for different solutions. And of course, as always, ask questions. If you have any, I will try to answer them. And thank you for watching. See you in the next videos.